All right, so you need it to be 2,000 milliliters, so I get it close to this line, and then we'll finish it off here. All right. I usually tilt this over so that it reduces spilling. Sometimes this can splash out. And then just make sure you line up the pegs with those divots. Okay. All right, that's ready to go. Okay, we have these tongs we can use. So in the top of the knurled ring that closes this down, you'll see there's a hole there, and there is another hole on the other side. We can use those to pick this up. Remember, we want to keep it as careful as possible so we don't lose that, the sample or the benzoic acid tablet. And what we're going to do, this seats into a little depression in that chamber, and we just want to make sure we put these electrodes in as it's going down, okay? And if you need help, just let me know. And these should be a little, you should feel some connection there, a little bit of firmness. And if there's not, we need to adjust the tightness of that. Now, there may be a little bit of oxygen that comes out, and that's okay. If the electrode comes out, that's okay too. You put it back in. All right. All right, so if you have a little bit of air come out, that's okay. If you have a lot of air that continues to come out, then maybe we need to check one of the O-rings or something like that. If it's a failed run, definitely we need to reassess and see what's going on. Okay. All right, so at this point, we are ready to start. So we just filled it with water. That's step operating the calorimeter on page 5. That's step 2. Okay, fill the calorimeter with water, and then we put the bucket in the calorimeter, and now we're going to put on the jacket. Okay, so the jacket goes right here, and there is this place where it just sets in there. Okay. Then there is a little piece of almost like a rubber band here that goes and connects the motor to the stirrer, okay? And then here is our high precision thermometer, and be really careful with this. It's kind of old, so it's got some bends in it, and that makes it hard to get through. What I'm using right now until I get that fixed is a little piece of foam right here, because I want to make sure we insulate that hole. Okay. All right. And I'm just going to put that on there to keep it insulated. All right. So now it says let the stirrer run for 5 minutes. Okay. We need to go ahead and connect our stirrer and connect the ignition unit and go ahead and turn on the thermometer. So if you see, the thermometer is going to give you 3 decimal places of precision, okay? And to turn on the stirrer, you just go to the right, okay? And if you look at the instructions, it says just let it run for 5 minutes. Okay. After 5 minutes, then you're going to let it run for 5 more minutes. Except for this time, you're going to record the temperature. You record the temperature every minute for 5 minutes. So that's 6 recordings, right? Your initial and then 5 more minutes, okay? At the end of that 6th measurement, that's when we push the ignition button. At that point, okay, that's step 7, okay? And then step 8 and 9, it says, hey, you're gonna measure it every 15 seconds until you hit the 60% or 5 minutes. So I just tell people every 15 seconds for 5 minutes, and you're definitely gonna get that value in there. So 5 minutes for once a minute. Hit the ignition, 5 minutes recording every 15 seconds, okay? Then after that, we need 5 minutes of a consistent slope. So it may take an additional, so we're 10 minutes in, it may take an additional 5 or 10 or 15 minutes, but you're going until you have 5 minutes at a consistent slope, okay? Meaning that the temperature might be decreasing 0.001 or 0.002 or 0.05. Whatever it is, it needs to be the same change every minute for 5 minutes. Then you're done, okay? At that point, you can move on to pulling, disassembling everything, taking out, collecting the fuse wire, collecting the water we put in the bomb, and you're ready to move on to the titration, okay? All right, so, and there is a timer here. You can use that if you want to, or if you have a watch, that's fine too, okay? Do we want to keep going? I mean, I'm going to keep doing this. If you want, you can pause it and then pick back up, or whatever you want. Okay, at the 5 minute mark, we're going to record the temperature, and then we're going to keep going until we get to 10 minutes. So I'm going to record it once a minute, okay? So I'm going to have my initial temperature and then once a minute for 5 minutes. And so my initial temperature is 18.685. It just went up to 686, but when I saw it, it was 685. Now remember, this is all in your lab notebook. I don't have a lab notebook, so I'm doing it on this paper here. But this all goes in your lab notebook. We don't transcribe it later. We don't say, hey, I want to make it look pretty later. No, it's supposed to look messy, and it all goes in your lab notebook.
Good to know.
Yes, a student spilled some liquid on their notebook today, and they were upset. And I said, look, that to me tells me it was actually used as a notebook. If it looks too pretty, it makes me wonder if you actually used your notebook. So it's supposed to be messy. All right, so 18.687. Okay, and the math we have to do with this is part of the temperature rise and temperature corrections, which is on 8, okay? So it's nice if there's no slope, that just becomes the change in temperature. But if there is a slope leading up to it or at the end, they tell us how to deal with that. And if you have any questions about that, I'm happy to help, and maybe that'll be on the video. So 18.689. 18.691. Okay, so if you turn this on at your initial point, then the times of 5 through 10 are your first measurements, and then 10 through 15 are that rapid rise period. So I go ahead and label that out so I can go ahead and write it down as it happens, because everything's going pretty fast at 15-second recordings. All right, 18.693. All right, so that's 18.694, and I'm going to hit the ignition button and then at exactly 10. All right, I hit and held that down for a second, 18.694. And now I'm ready to start recording these temperatures. $18.699. $19.063. $19.589. $19.944. $20.262. $20.493. $20.691. You see it starting to slow down. Okay, so now I'm going to do it every minute, all right? So, and what you want to do is you want to go until the difference between two measurements is the same 5 times in a row. So here it looks like it's hit a maximum and now it's starting to cool down a little bit. So now I expected fingers.
Yikes.
Okay, so that one changed from 356 to 355 right on that minute mark. So if it was me and I was trying to get it exactly right, I would be okay calling it either one. You know what I'm saying? Depending on which gave me that better result, because it changed right on that value. And I'm left with that precision, so I can't say and a half. Okay, this one seems to be oscillating back and forth. And so if you get to that, I would call it there too. If it's oscillating between two values for 5 consecutive times, then I would go ahead and call that, because again, there's uncertainty in that very last digit. We know that. So anyway. So based on how we called that, that could have been a 4, that could have been a 4, and that could have been a 4 based on those numbers. So I'm going to call it there. So we have the 4, then 2, then 4, 4, 4, 4, because of that oscillation and that uncertainty of that last digit. So we'll say that the difference is 0.004, and we'll call it right there. And then the final temperature is 21.341. Okay. All right, so we'll stop it there. Now what we need to do to turn it off is we'll go ahead and turn this off by turning it to the right. It always goes to the right. I'll take this off. Part of that up and down that we get is because the thermometer, I need to replace that. It does no longer fit through this port right here. So, all right, anyway, pull out the thermometer. We can take off this rubber band, set it aside, take this off, set it aside, okay. I'm gonna go ahead and unplug everything since we're dealing with water. You can take out the electrodes, okay. And you can put this in there, but you can also just reach in and grab it. And then pour off that little water. Now it doesn't matter if the cup gets out of place. And we'll put that down. We want to get a paper towel and dry that off. I'm going to dump this out and dry that off. And then I'll show you the last two things we need to do. Okay, we do have metal, we do have water, so even though it's stainless steel, we want to go ahead and just dry these things out, just so that we reduce the amount of corrosion that we can get. So just go ahead and dry that out, and then you can set that aside, ready for the next time. Okay. Same thing here. Let's go ahead and dry this off. Okay. The best that we can. Okay, now this is still pressurized. It still has, has pressure in there from the oxygen and any combustion gases. Okay. So we're going to loosen this right here. Watch out, there may be some water in there, so it may spray a little bit. Okay, also, depending on what you combusted, it may be nasty. So we'll go ahead and loosen that. So now we got to take this ring off. Okay, and then I usually try and grab it by putting my fingers around these posts as good as possible, and then I'm doing a rocking motion as I'm pulling that up. Okay. And then what you should see is usually there's basically nothing left in that cup. We combusted that tablet in its entirety. Usually that's the same thing you see for your food. If there is a lot of food left, then you didn't have enough oxygen, maybe there was a leak, maybe you need a smaller sample size, something. We'll need to revisit that there. Okay, now we need to do two things, okay? One, we need to collect any fuse wire that was not combusted, okay? Because that affects your calculation. So if there's any fuse wire that was not combusted, we need to collect it and measure it the best of our ability. So there's a little bit there, and I usually put it down in this little weigh boat until I'm ready to deal with it. Okay, so I don't know if you can see that, but there are two small amounts of fuse wire. We'll need to measure those. I think I said weigh. We need to measure those. They affect one of the calculations, okay? All right, so we're done here. Again, just make sure everything is dried off. Okay, especially if you're done for the day. Make sure everything is nice and dry, as good as possible. All right. All right, then the last thing we need to do, aside from measure that distance, okay, is we need to collect the water that's in there because we need to titrate that, okay? So you'll want to collect it in a beaker and possibly parafilm it. Since I'm just doing this for a video, I'm going to collect it in this right here, and I'll put a little parafilm over that. Okay, so all right, this is my deionized water. I'm going to go ahead and use some water and rinse down the sides in case there was anything on the sides. It doesn't matter if you have more than 1 milliliters here. You don't want to go crazy, but okay, then this does not pour the best, so I'm going to now collect it here. Okay, so this we need to save and we need to titrate it, okay? So let me go over what we have left to do because we're not going to do that in this video. We'll make another video about it, or you can just talk to me about it, okay? All right, so you want to look at 3 calculations, okay? Here on page 8, you have a lot of your definitions, and this is a really great example. Just go by this. That's what I do every year when I look at it and haven't thought about it for a year. Then your sample calculation is on page 9, and your calibration calculation is on page 10. So that's what we would use here. Okay, W is the energy of the calorimeter, okay, and that's going to be in calories per degree Celsius, and usually we convert that to kilocalories per degree Celsius, okay. H is the heat of combustion of standard benzoic acid in calories per gram. So calories per gram at 6318. You can see they have 6318 right there. M is their mass. They used a tablet that's 1.1651. I would put in 1.0249 because that's what I massed out. Then correction E1. E1 says correction for heat of formation of nitric acid in calories. What's that? Okay, well, what you have is when you're doing that correction, let's see, you have, they tell you how to do with that one, how to prepare that solution here. E1, correction for calories, formation of nitric acid, and this is if you're using 0.0709 normal sodium carbonate, then that's just going to be the milliliters, okay? The milliliters is going to be the same as calories, all right? So if you look in the example they used, they have 11.9 milliliters they used in their titration, and it's 1 calorie per milliliter if you used that concentration sodium carbonate, okay? And that gives them a total of 11.9 calories. So as long as you use that correct value, and they tell you how to make that here in 15. So titrate bomb washings with standard sodium carbonate and use methyl orange or methyl red as the indicator. This is what they want. And if you dissolve 3.76 grams of sodium carbonate in 1 liter, okay, then you have this concentration. So they even tell you how much of sodium carbonate to put in 1 liter, okay? And then I usually use methyl red as the indicator. So when you do that titration, E1 is just the milliliters, okay? Then we have E3. E3 is the fuse wire correction, okay? So this is the length of fuse wire that we used, okay? We used 9.95 centimeters, and then what we would do is we would subtract, I would measure this, the length of these two pieces, and I would subtract that from 9.95. Whatever that distance is, then we multiply that by 2.3 calories per centimeter, okay? So we take our 9.95, we subtract out those two, the length of those two pieces, and then you multiply it by 2.3 calories per centimeter. And that gives you correction E3, okay? And then T is your temperature, okay? And so that you need to get from the temperature rise. So the temperature is going to be TC, okay? And so TC is the temperature at time C. Time C is the time at the beginning period after the temperature rise in which the rate of temperature change has become constant. And TA is the time of firing, okay? Temperature at the time of firing. So temperature at the time of firing, TA, is 18.694, okay? And temperature at the beginning period where this leveled off, I would go back to 21 and call that 21.356 because it's at the beginning of that time period. Actually, I'd call them back to 20. 21.358. 21.358 would be the temperature at the beginning of that 5-minute period, okay? If you don't have a slope, then it's just those two, the difference between those two numbers. If you have a slope, you have to do this little R1 B minus A, R2 C minus B. I can help you with that. It's not as hard as it looks, and it's a small correction factor, okay? And so then you just throw those things in this formula and it gives you your calibration. Good? Then I can help you with this, but again, this is your sample. Same thing, they show you exactly what they're doing. They're really good about giving you example values, but I'm happy to help you with all of that. Okay? All right, so we did everything. We did not do the titration. We did not do that, but I told you how that works, and I'm happy to help you and show you in a different video, but I think we've done enough on this video, and hopefully you have a good idea of how to do the experiment. All right, thanks. Bye.